Yes, I am with you guys. Okay, cool. Let us start. I will open the chat up in a second. Okay, before we start, please confirm with me that you, okay, let me open the chat so you guys can talk to me. Please do confirm with me, however, that you can hear me clearly, that you can see my screen, that you can see me, and that everything is working A-okay. Please let me know on YouTube as well. Good people. Good grade 11s. Okay, firstly, I apologize for being late. These past few lessons have just been a bit late and continuing a bit over time. But nevertheless, we are here. Okay. Okay, then we can get started. Send everything to the group. Yes. Perfect. Okay, so Assalamu alaikum and good morning. Welcome back, everyone. Actually, for those who are maybe joining us this week, welcome. My name is Abdullah Ali, and I am your tutor for grade 11 physics. Okay, so today we're going to be continuing Newton's. Okay, it's quite a big topic, so I want to make sure we take our time with it and complete it so that you guys understand it, right? It's no use us rushing through it to get through syllabus and we don't understand anything. Okay, so yes, please, if you guys do have any questions, feel free to ask them in the chat using the Q&A feature or utilizing the YouTube chat for those of you who are on YouTube. Okay, cool. Let's get started. So remember we discussed vectors, okay, vectors in 2D, mainly with vectors, especially going into grade 12, right? So obviously at the end of grade 11, your grade 11 marks are extremely important because you want to use those marks to get provisional acceptance for grade for university, right? So you need to know your vectors for grade 11, right? Because in the grade 11 final exam, they will be testing you questions on vectors. Okay, however, for grade 12, you will not need to know vectors specifically. However, the understanding of vectors, you most definitely need to know. Okay. But yeah, just give me 1 second. Basically, I want to go through a vectors question before we move on. Okay, let me just get the memo. Okay, cool. So yes, right, what's important with regards to vectors is understanding head to tail, okay, definitely resolving into components on a slope, extremely important, especially going into Newton's head to tail method, okay, as every vector, resultant vector, okay, Pythagoras, utilizing Pythagoras, okay, and trigonometric calculations to work out the value of the resultant vector, right? And just the understanding of vectors as a whole, how they have magnitude and they have direction, is extremely important. So let's do a question where it's only it's vector components. It's basically you're testing your understanding of vector components. Okay, so this is an Eastern Cape November 2020 grade 11 final paper. Okay, a pulley system is used to keep a crate of mass mkg stationary. Okay, it's used to keep it stationary as shown in the diagram below. Okay. Define the term resultant vector. So remember, the resultant vector is a single vector that has the effect of two or more vectors acting together. So here's it, a single vector which has the same effect as original vectors acting simultaneously on an object. And remember, we described it as if you are moving 9 meters east and then 5 meters south, so sorry, 5 meters north, you could have just moved that much diagonally and you would have experienced what is going on? You would have gotten to the same place. You would have actually experienced the same displacement. So that is the black vector is actually the resultant vector. It has the same effect of those two vectors working together. Okay, calculate the vertical and horizontal components of T2. Okay, so let's look at what is going on. Okay, so let's look at this diagram and see what's going on. So we have a box, okay, attached to this point, okay, which attaches all the tension ropes. So we have one rope across a pulley and another rope across another pulley. Okay, so just remember, just note actually in Newton's, when in general, when it comes to pulleys, okay, the pulley does not affect the tension in the rope. It's a frictionless pulley. It is not on my screen. Is the screen frozen? We can't see. Apologize. On my end, it was sharing, but it was frozen on your end. Okay, can we see now? Okay, perfect. Sorry about that. Cool. Okay, so yes, this is the question we're working with, right? So we have this system, okay, where the box is connected, and we have two tension ropes. So what I was busy explaining was that you need to note that when we deal with Newtons, when we deal with pulleys in the section, the pulley does not affect the tension in the rope because it is a frictionless pulley. Okay, so in this case, for example, what is going on? In this case, for example, there's 245 newtons. That is the force of the tension on this rope is the same force that's carried over to that end of the rope. So basically, it is in that direction. Tension in the rope is as like that. Okay, English. Okay, the tension in the rope, the direction of that force is in that direction continuously. So just because it goes around the pulley, it changes from going upright to down. Okay, but the actual value for the tension in the rope does not change. So that means that this here, the tension, this tension here, okay, is 245 newtons, just like that. Okay, firstly. Now, they want us to calculate the vertical and horizontal components of T2. So remember, this is a diagonal force, the tension force in the upright direction. In this case, our diagonals are regular diagonals, vertical, that's our vertical, and that's our horizontal axis, right? We're not on an inclined surface or anything like that. So in that case, right, remember the easiest way to tell which direction are my components is to describe the direction of the force to yourself. Describe the direction of the force to yourself. In this case, this tension force could be described as a upright force. So in that case, our components are going to be up and right. Upright force, in that case, our components are going to be up and right. Okay, I hope that makes sense. Our vertical component is up, our horizontal component is right. Remember, these are the original one. What is going on, man? The original one. The original one actually kind of acts as a resultant vector because when you combine these two head to tail, I know I didn't draw it perfectly, so that's why it gets there. But technically, that's also correct because that force is like there as well. It's the same thing. But the original force actually acts as a, when you move it across this way, it acts as a resultant vector. Okay, so we're actually going to leave it like this. I'm going to erase this and draw the force there. Maybe let's use blue. Just like that. Okay, so this is actually like a resultant vector. So whenever we separate it into its components, we use this triangle, this 90-degree triangle, to help us to calculate the value of these components. In this case, we have a 90-degree there. We have this angle, and we're going to use our trigonometric ratio, sine, cos, tan. Okay, so now they want us to calculate the vertical and horizontal components of T2. So T2 is what? T2 is opposite our 90. So T2 is actually our hypotenuse. Resultant is always the hypotenuse. Now, we have this angle, okay? Now they want us to calculate the vertical and horizontal component. So let us call this T2y for vertical and T2x for horizontal. T2y for vertical, T2x for horizontal. And if we have to calculate the vertical first, okay, we need to describe the vertical in terms of the angle, and it is its opposite. Okay, so since it's its opposite, we're going to use sine. Sine 30 is equal to, remember, sine is opposite over hypotenuse. Sine theta is equal to opposite over hypotenuse. So T2y over T2 itself. Okay, I hope you guys are with me. Vertical component of T2. Firstly, we created an up component and a right component because it's an upright force. Secondly, I moved the up component to complete the triangle. I drew head to tail method where I have the actual force, which is T2, the diagonal force, as a hypotenuse to create this trigonometric triangle. Okay, and that's how I'm going to calculate my values. So in this case, if I want to calculate T2y, I need to take T2 to the other side. So it's T2 times sine 30, which is going to be equal to T2y. But you don't have to do this. You don't have to show this. You can directly show that. It's fine, right? Because you know it's opposite, you're always going to take sine that angle, okay, and multiply it by the actual force. Generally, it's like force's component is equal to that force multiplied by sine the angle. Okay, so if I want to calculate the vertical T2y, because it's opposite, it's going to be sine 30 times, remember it's times T2. In this case, T2 is 245 newtons. When I do this calculation, T245 times sine 30 is T2y is 122.5. Like, I am not doing that. Newtons. Let's do the horizontal component. The horizontal component, T2x. Okay, somebody tell me an equation to calculate the horizontal component. Remember, this is the horizontal guy. We have to express it in terms of our little triangle. Okay, cos 30, that's correct because it's adjacent. How do we get 245 for the vector acting at the angle? Okay, so that is given. If you look in the question, here it says 245 newtons upon this rope. Okay, and I was saying that the force on the tension rope does not change. Okay, because it's a frictionless pulley. Okay, so please note that. 1 second. So that's true, that works. Okay. So yes, all of you are correct. Very good. You're going to use cos 30 because it's adjacent. So cos 30 times 245, which is cos 30 times, let's write it out this time because we didn't write it above. So cos theta times T2, which is equal to cos 30. Cos 30, sorry, just forgive the pen just for today. I'll try and get it sorted out. Cos 30 times 245. When we do that calculation, we get an answer of 212.18 newtons. Okay, so that's components. Calculate the magnitude of T1. the magnitude of T1. Now, obviously, we have to relate T1 to this point, right? So it goes down in that direction, but when relating it to the point, we can actually see that it would be a, it would be a left force. Okay, now in equilibrium, which technically this is equilibrium, meaning it's stationary, right? All the forces balance each other out. Okay, what you need to remember, we'll go through it in an equilibrium question, but this is in terms of vectors, which we need to know as well. Because it's stationary, okay, all the forces balance out. Now, all the forces in the vertical plane balance out, vertical, okay, and vertical forces are basically up forces. So your up forces are equal to your down forces. Okay, and all the forces in the horizontal also balance out because it's stationary, horizontal. So your left forces are equal to your right forces. Correct, which we've already technically done. We found T2x, okay? YouTube people, are you guys okay? You guys are a bit quiet. Okay, so horizontal is left is equal to right. So now, and we'll get to also free body diagrams, if we have to consider in this case, right? We have, I'm just going to write a little free body diagram just to represent all the forces and like what they components. So currently, instead of having T2 as a diagonal force, I'm going to put T2y, which is what we have. Come on, man. T2y, okay. And we also have T2x. Okay. We also have FG. Okay. And to the left, we have T1. How do we calculate magnitude? How do we calculate magnitude of? Sorry. Is T2x equal to 245? No, T2x is not 245. Right? Let's compare the difference. 245 is actually just T2. T2 itself is somewhere here. Let's draw it in dotted lines. T2 itself is somewhere here. This is T2. This is 245. Okay. T2y is its vertical component and T2x is its horizontal component. Okay. So the diagonal one is 245. How do we calculate the others? We utilize that trigonometric triangle, the Pythagoras triangle. We move this over here, okay? And we create a 90-degree angle and we use sine and cos to calculate the values respectively, provided that we have this angle, which is actually 30, if I'm not mistaken. Yes, I don't understand your question. How do we calculate magnitude? What magnitude are you specifying? Which magnitude are you talking about? Okay, so the magnitude of T1, magnitude, okay. If you want to know what is magnitude is just the value, okay, the numeral amount, okay, the value of it is 5, 10, 23.6. So T2y would be equal to the normal force. Okay, there's no normal force here because it's not on a surface, okay, but we'll get there. Let's just talk about T1. T1 in itself, remember we said it's stationary, so left forces are equal to right forces. In this case, I have my left forces, I have my right forces, so therefore I can calculate, I can say that left forces are equal to right forces. Left is T1, right is actually T2x, as we can see on our little free body diagram there. Okay, T1 and T2x. So T1 is what we want to know. T2x, we actually calculated. T2x is 1.225 newtons. So that's why it's a 2-mark question, because we already calculated the value of it. 122.5. This right force is equal to that left force. That's always the case when things are stationary. Again, we will eventually do an equilibrium example. Calculate the mass of the crate. So now we're going to use the up is equal to down aspect of it being stationary. Our up force is T2y. Our down force is Fg. So in this case, up, hello, there we go. T2y is equal to Fg. Firstly, T2y, we calculated, it's 212.18, Yeah, 212.18, which is equal to m times g. Remember, Fg is m times g. In this case, m is unknown, but g is gravitational acceleration, which is 9.8, and is equal to 212.18. We take 9.8 over to get the mass of the object as 12.5 kgs. Okay, so that's just a calculation for vectors. And repeat magnitude again. So magnitude is a value. To ascertain a value to something, how much is something, that would be the magnitude. Okay, so if you are pouring 2 liters of water into your glass, the magnitude is 2 liters. Okay, if there is, okay, how we distinguish the vector quantities have magnitude and direction. So that's a good example to use. Velocity, for example, if I would have to say velocity of negative 15 meters per second, in that case, the magnitude is just 15. The direction is actually indicated by the negative. T2x is 212.18. Yeah, you are correct. This is supposed to be cos. No, it's not supposed to be cos. What's the issue? T2x is cos. Is my calculation incorrect? T2x horizontal and T2y the vertical? Yes, indeed. Sign is opposite. T2y cannot be wrong. Yeah, okay, sorry, this is supposed to be T2x. Oh, I see. Sorry, the spin that's not working is throwing me off. But yeah, I get you guys. There we go. Okay, I think I fixed everything. T21 is shown acting down. T1 is shown acting down. Why do we take it as acting horizontally? Okay, so because we're working from this point, everything we are working with is working from this point because this is where all the system pulleys are. This is where all the ropes are connected to. Okay, so basically, it's a continuous tension along this route. Okay, if you can see, it continues downwards. Now, even though the tension is shown as downwards, remember it stems from here, and the pulley actually makes it face downwards, but it actually routes from the rope, which is connected there. So the tension is in this direction, just like that. So it is the exact same tension on every part of the rope. However, it's not as if it's connected to this point downwards. It's not. It's connected to this point in a horizontal direction. That's why we take it to the left. How did you get 12.5 kgs? So up forces are equal to down forces. T2y is equal to Fg. Where are we? Where is T2y? Yeah, T2y, okay, is equal to Fg. T2y is equal to Fg. Okay, so in that case, up forces are equal to down forces. So that's how we created the equation. And then T2y we calculated as 122.5. We equated it to m times g, which is the calculation for Fg. And we divided both sides by 9.8. And that's how we got 12.5 kg. Okay, hope that makes sense. Okay, so that's the vector equation done. Let's move on, right? Let's talk about Newton's first law. So I decided to just restructure it a little bit and separate it. Let's go through Newton's first law and do an example. So Newton's first law of motion, we went through them yesterday, but now we're going to be going, not yesterday, last week, but we're going to be going through them again. So Newton's first law of motion states that an object continues in a state of rest or alternatively uniform motion, moving with constant velocity. That's what uniform motion means, unless it is acted upon by an unbalanced or a net force. Okay, a net force is better, right? Okay, unless it is acted upon or it is, or unless a net force is applied to it. That's another way of saying it. Newton's first law is due to inertia, which an inertia is the object's resistance, the resistance of an object to change its state of rest or constant uniform motion. We'll go through that in a bit. Now, Newton's first law, it's important for us to note that F net is equal to 0 newtons, okay? And that A is equal to, the acceleration is 0. Okay, we'll come back to those concepts. We're going to actually do a little bit of theory on Newton's second law and come back to first law. The importance of wearing safety belts, this is Newton's first law. According to Newton's first law, an object will remain in motion at a constant velocity unless a non-zero resultant force acts upon it. When a car is in an accident and comes to a sudden stop, the person inside the car will continue with a constant forward velocity. Without a safety belt, the person will make contact with the windscreen of the car, causing severe head trauma. The seat belt acts as an applied force, preventing the forward motion of a person. So basically, if you are traveling at 120 kilometers per hour and you meet up in an accident, you bump into someone, of course, your car is going to slow down. Maybe your car slows down to literally in a few seconds, even 0 kilometers per hour. If you're traveling at 120 kilometers per hour and all of a sudden, let's say in 1 second, your car stops, let's just say in 3 seconds, your car stops, it comes to 0 kilometers per hour. In that 3 seconds, because it's such a short time, okay, you are traveling at 120 meters per second, 120 kilometers per hour. Your car is traveling at 120 kilometers per hour, and so are you, the person in the car. So because of that, your body wants to continue traveling at 120 kilometers per hour. So if the car all of a sudden stops, your body is going to want to continue to travel at 120 kilometers per hour, and that's why you will fly out the windscreen, okay, if that happens. Okay, that's why we need a seatbelt to hold us back, to stop the inertia, basically, of the tendency to want to continue at that same speed. Okay, so that's important of seatbelts. Let's discuss inertia. Okay, inertia is the property of an object that resists any change in the state of rest or uniform motion. Okay, it doesn't want to change the speed at which it's traveling at, the human body. Okay, if the object is at rest, it resists any change to the state of motion. If it's in motion, it resists any change to the speed and direction of its motion. Inertia is determined by the object's mass. The greater the object's mass, the greater its inertia. Example, a box lying in the boot of a car will move forward when the car brakes. Okay, the box inertia resists the change in movement and allows the box to continue moving in the direction in which the car was moving before it stopped. This is why you must wear your seatbelt. Okay, we'll come back to this example in a bit. Let us move on to discuss Newton's second law. Newton's second law, when a net force, so Newton's first law, remember, an object, if you fly through the windscreen, it's due to inertia. Yes, it is definitely due to inertia. If you hit brakes hard and you move forward, okay, if it's extreme and you're traveling really fast and then you brake really fast and you're not wearing a seatbelt, your body will try to continue at that speed it was, and you can hit the windscreen, or potentially you can break through the windscreen and fly out of the car. Okay, so yes, that is due to inertia. But when you wear your seatbelt holds you back and stops your body from moving forward. Okay, Newton's second law, when a net force is applied on an object of mass, it accelerates in the direction. It accelerates in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass. Okay. When a net force is applied to an object of mass, it accelerates in the direction of the net force. So if the net force is applied to the right, the object will accelerate to the right. And that acceleration, you need to note, is directly proportional to the net force, while being inversely proportional to the mass. So the higher the net force, the higher the acceleration. The higher the mass, the lower the acceleration. Newton's second law is dependent on the resultant force, the vector sum of all forces acting on the same object. So now this is really important. We know F net. F net's formula, F net is equal to M times A. This is what we use for Newton's second law. The net force on an object is equal to the object's mass times the object's acceleration. Okay, so that's really, really, really important. That's what I wanted to just note, that formula. Let's go back to Newton's first law and let's discuss this. Okay, so firstly, why is F net equal to 0? Firstly, F net is equal to M times A. Okay, and A is 0. Why is A 0? Because remember, Newton's first law states that the object wants to continue in the state of rest or constant velocity. Remember, constant velocity has 0 acceleration because firstly, distance or displacement rather is the distance between start and end point. Velocity is change in distance. Okay. Velocity is change in displacement, and then acceleration is change in velocity. Okay, so the rate at which we are changing our distance is velocity, meaning when you say your speed is 5 meters per second, it means that every second you are moving 5 meters. So the rate at which you are changing your distance is 5 meters per second. Okay, and the same applies for acceleration. Now, acceleration is the rate at which you are changing your velocity. If you are speeding up and speeding down, if your acceleration is 5 meters per second to the -2, that means that every second you are increasing your velocity by 5 meters per second. However, when you are at rest, firstly, at rest, there's no velocity. So therefore, there can't be any acceleration. At rest, there's definitely acceleration is 0. Okay, at a constant velocity means you're not changing your velocity. So if you're not changing your velocity, you're not going to have acceleration. Okay, I hope that makes sense. So when there is constant velocity, acceleration is 0 as well, because you are not changing. Remember, acceleration is the rate of change of velocity. If you are not changing your velocity, then you have no acceleration. So that's why at a state of rest or constant velocity, acceleration is 0. Therefore, F net is equal to M times A, which therefore results in F net being equal to 0 because A is 0. Okay, cool. So that's Newton's first law, F net is equal to 0. So let's have a look at this diagram. This diagram shows the forces on a trolley moving with constant velocity. Okay, so before we discuss that as well, I want to discuss how do we open up F net. Firstly, F net, this F net, okay, only applies, okay, that's not technically true. Yeah, but let's just write it, only applies. This is for Newton's second law mainly. Only applies to forces parallel to the direction of motion. Okay, then you'll see algebraically, how do we open up F net? Okay, we always say, okay, forces in the direction of motion. Direction of motion is the direction in which the object is traveling, minus forces opposite to direction of motion. Okay, forces in the direction of motion is F net all forces. Okay, that's an interesting question. So F net is basically this. It's basically this calculation. It's when you consider all forces. Now remember, some forces may be in the right. Okay, let's just say we're working in the horizontal plane. Some forces may be in the right direction. Some forces may be in the left direction. In that case, you take whichever is the bigger one, right or left. You say the bigger direction minus the smaller direction, and that's going to give you an overall net force. Let's do a simple vector example, right? if I have a vector that's going to the right, and I have another vector that's also going to the right. Okay, if I want to consider the net force, because they're in the same direction, I will add them together. And when I add them, in this case, I can say F net is equal to 1 plus 2. However, just say I have one vector in the right direction and another vector in the left direction. In this case, I would have to say F net is equal to 1 minus 2. So now in this situation, actually my net force is just, because it's to the right bigger than to the left, my net force is just the difference here. This is F net. Okay, so yes, it is all the forces. What is your question exactly? Is it all the forces? Yes, it's when we consider all the forces, but it's not necessarily like combined. You're just always going to add them all up, right? F net could be smaller at times as well. Okay, so just keep this in mind, that F net is equal to forces in the direction of motion minus forces opposite to the direction of motion. Okay, so let's have a look. Now, the diagram shows the forces on a trolley. So remember, we're back to Newton's first law, where there's no acceleration. Objects want to continue at their state of rest and constant velocity. So the diagram shows forces on a trolley moving with a constant velocity. As soon as we see this, we need to note acceleration is 0. Why? Constant velocity. There's no change in velocity, right? Newton's first law. A man pushes a loaded trolley with a constant velocity, again, constant velocity, no acceleration, along a horizontal floor. The trolley and load have a mass of 56 kilograms. So we know the mass of the object, and the friction of the moving trolley is 2,1 newtons. Calculate the force the man exerts to push the trolley along the floor. So firstly, look at this free body diagram. Is technically drawn. It's like a force body diagram. We have the normal force, we have the weight, we have the applied force, and then we have the friction to the left. Okay. Remember, we described friction as it always opposes the direction of motion. So friction is always opposite to the direction of motion. So in this case, we are going to do an F net is equal to M times A. F net is equal to M times A, right? And then we are going to say F net is equal to 0 because there is no acceleration. Is that calculating F net graphically with vectors? Yes, that's what I was basically displaying. Okay, so F net is equal to 0. But now, how do we open up F net? Remember, it's forces in direction of motion, DOM, minus forces opposite to direction of motion. Okay, that's how we open it up. In this case, it's equal to 0. So tell me, what is the direction of motion in this specific question? No, we do not need to calculate FG first. What is the direction of motion in this specific question? Applied force, which is to the right, correct? It's to the right, okay? That's the direction of motion. So all my forces in the direction of motion, I'm going to combine them and subtract all the forces opposite to the direction of motion combined. In this case, it's going to be applied minus friction, because that's the force opposite to the direction of motion. So it's going to be F applied minus F friction is equal to 0. So I can now substitute values if I'd like, because I need to calculate F applied, but I have friction. Friction is 2.1. So actually, I can take it over. F applied is equal to F friction, because when I take it over, it becomes positive, and 0 plus FF is just FF. So therefore, F applied is actually equal to 2,1 newtons, because it's actually, because it's constant velocity, it's equal, because it's constant velocity, it's equal to the friction opposing it. All right, it's moving at a constant velocity, all the forces balance each other out. So calculate the force the man exerts, which is the applied force. That's what we just did. If he then pushes the trolley with a force of 2.5 newtons to the right, calculate the acceleration of the trolley. We're still going to use F net is equal to M times A. But now it's not Newton's first law. It's Newton's second law, okay? Because there is an acceleration. In Newton's first law, there is no acceleration. Now he's applying that extra 2.5 newtons to the right, Okay, so now the applied is 2.5. So F net is equal to M times A. How do I open up F net? Forces in DOM minus forces opposite DOM. And this is equal to M times A. Now, M times A is not 0 because now we have an acceleration. Forces in direction of motion is applied minus forces opposite to the direction of motion is friction is equal to mass times acceleration. Now, okay, F applied, we said he pulls with a force of now 2.5 newtons. So 2.5 minus friction stays as 2.1. Okay, mass, we said the combined mass of the trolley and the load is 56 kgs, which we will leave in kgs. 56. Acceleration is what they want us to calculate. So this is 0.4 is equal to 56a. Take 56 over, we divide both sides by 56. We get acceleration as let me just see if this is correct. Okay, but I'm just going to put it in decimal form 0.007. Very, very slow acceleration. Acceleration is to the -2. One second, I just want to confirm our answer. If anyone did the calculation, please confirm with me that it is correct. Yeah, it is indeed correct. Okay, it's a very slow acceleration because, I mean, he's pushing up 56 kgs. Or he's pushing 56 kgs, and his applied force is barely bigger than the friction. Okay, so the acceleration is slow. Remember, it's times seconds to the -2. All right, so that's Newton's first law. Great, I'm happy with that, right? Let's move on to learning our free body diagrams and force body diagrams. So now we have a bit of a more complicated question. So we're going to draw the force body diagram and the free body diagram for each box respectively. Okay, so firstly, we're going to draw this force body diagram. So with your force body diagram, you need to actually create a box. Okay, to represent the object. Okay, whatever, it's not like perfect, but whatever. So we need to draw a box to represent the object. Why is F applied equal to 2.5? Because they told us that he then pushes the trolley with a force of 2.5 newtons to the right, which is now an applied force. With a times 10 to the power -3 at the end. Okay, so instead of writing 7,14 times 10 to the -3, that would be meters per second to the -2. This is the unit. It's different to the actual magnitude. I just wrote it in decimal form. Okay, so this is alternate answer. Your calculator is most likely going to give you scientific notation. Okay, so that's all the same thing. Okay, so firstly, you need to note force body diagram. So your first thing you're always going to have is your FG from the center of your object going downwards. Why are you not working with me? Going downwards. This is your FG from the center of the object. Okay, then you're going to have, okay, somebody tell me, guys, tell me what are the forces on this object? One is Fn, okay, so let's work with Fn. Now, Fn is always perpendicular. Remember we learned it last week. Fn is always perpendicular to the surface. Fn is always perpendicular to the surface. Fn only exists if the object is touching the surface. Fn only exists. Is Fg going to always be down? Yes, always in a force body diagram, free body diagram, to get your marks for the diagram straight down. Got it? Fn is always perpendicular to the surface. So in this case, you start from the surface. On your force body diagram, you start from the surface with your Fn, and you go perpendicular-ish to the surface. And you draw a force like that, and you call it Fn, normal force. Let's see what other forces we have. We have Fn, Fg downwards, tension. Okay, great. We have tension. Which direction is tension? Can you please give me a general direction for this tension? Okay, Fg parallel, Fg perpendicular. I'm not splitting it into its components just as yet. Okay, remember in the force body diagram, you don't want to split it into its components. You just want to draw it as Fg to make it as simple as possible. Right, that's not correct. Yes, we're working with the 5 kg block. Okay, technically it's not right. Yes, we do have friction, which I will add as well. It's not left either. Upright, yes, correct. Not southwest, it's not down. It's not both right and left either, okay? So whenever you're dealing with tension, tension is always wherever the rope touches the object, you go from the object, you start at the point where the rope touches the object and you go away from the object. Let's do it for the side. You start at the point where the rope touches the object and you go away from the object. That's the direction of tension. You can cut the rope if you'd like, and then create a force there and a force there. I don't know. Okay, yes, but technically it is upright. Okay, that's more correct. That's more precise. Or up the slope. Okay, you have to be precise when you're giving the direction. It's important. So up the slope. So we talked about tension. So whenever you're dealing with an applied or a tension, okay, wherever it is touching the object, you can show it on your force body diagram at that specific position on the object. However, Fg start from the center. Normal, you start from the surface. So our tension is going to be something like this. Parallel to the surface, we call this guy F tension. Okay, the last and final force is going to be our frictional force. Okay, remember it says here it's a rough surface, so there's always going to be the presence of frictional force, and this is going to be on the surface, at the back of the object on the surface, right? Away from the direction of motion. So down the slope. Okay, this one is being pulled up the slope. So this is going to be at the bottom, on the edge of the object, down the slope. This is our frictional force. Okay, and that is how we draw our force body diagram on the object. Let's look at the same 5 kg block, but the free body diagram. So just the dot. By the way, in matric, you will only be required to know how to draw a free body diagram, which is great, right? In grade 11, you will need to know the force body. Hey, that's a good question. That's a good question. Thank you so much for that. The question was, should we put direction? And the answer to that is yes for this acceleration question. Why? Because acceleration is a vector quantity. So if he then pushes the trolley with the force 2.5 newtons to the right, calculate the acceleration. Our answer will need to be this, to the right. Okay, thank you so much for that. I totally forgot about direction. Okay, because it is a vector quantity, it needs to be to the right. A man pushes the trolley, calculate the force. You see, even this one, calculate the force the man exerts. A lot of the times in the exams, they say calculate the magnitude of the force. So then you don't have to put direction because they just say magnitude. But because force is a vector quantity, in this case, we will have to say to the right as well. Thank you so much for that. Okay. Now let's do the free body diagram. So firstly, I'm going to start by always taking Fg downwards. Okay, so we take Fg downwards, right? Let's actually just use that. Okay, we take FG downwards, that's the regular one. We need 4 forces in total. Now, because we're at an incline, okay, step 1, actually, before we did this, draw your dot, okay. Step 1 is to identify your vertical and your horizontal. Your horizontal is always parallel to the surface. Horizontal is always parallel to the surface. So in this case, my surface is at a 45-degree angle to the slope, to the horizontal, sorry. So my horizontal is going to be just like this. Okay, that is my horizontal. My vertical, when we draw diagrams, does it have to be to scale? Not at all. It does not have to be to scale. Okay, it is not vectors. If you are drawing vectors and you are using a vector diagram to solve for a specific question, to solve for if they tell you to use a vector diagram to solve for the resultant vector, yes, in that case, it would have to be to scale because you need to measure. In a free body diagram, nope, it does not. It just has to be neat, please. Yeah, technically, you don't have to like draw this bottom piece, but you'd have to draw that surface, okay? And the main thing on the force body diagram is your position of your vectors, as well as you have to draw the object. Okay, you have to draw the object. Okay, with the free body diagram, you're not drawing the object. They're all going to come from the center, right? So let's complete our vertical, which is always going to be perpendicular to the horizontal. So something like this, right? This is you drawing this in pencil, okay, just for your own benefit, so that your vectors can be accurate. So now that I have my axes, my horizontal and my vertical axes, remember the horizontal and vertical axes are not like this for this question because we are on a slope. So our horizontal always needs to be parallel to the surface. It's not exactly parallel to the surface, but it's more or less fine, right? Again, it doesn't have to be accurate, like I said. Now, we start from this dot, and we're going to draw all our forces. So we have FG, always just go down. If you need to get marks, don't separate it into its components, just do one. You're going to get 1 mark per force. FG. Okay, when we do complicated questions, that is when we are going to separate FG into its components. When they ask you, please draw a free body diagram for object 5, the 5 kg object, my recommendation is do not separate anything into any components, draw them as they are, and then do another free body diagram when you're actually doing the calculation question. Okay, just to secure these marks. All right, let's do the next one. Let's look at this. Right, we have our normal force, which is perpendicular to the surface. So it is in line with our horizontal. Why are we drawing the broken lines? Okay, so the reason we're drawing the broken lines is to represent our vertical and our horizontal axis. Okay, first, so the first reason that's important is to show the accuracy of our direction of our vectors. So, for example, if I just had to have this and that, okay, and then F normal, and then FG, okay, then if you draw, just say you need to draw something that's up the slope, for example, F tension. Let's draw it like that. F tension. Okay, now it might be a bit of a rough drawing, but you can see these don't exactly look perpendicular. If you're going to draw your axis, it's going to allow you to draw that a bit more accurately and just to draw it neater and to depict it in a way that it actually looks perpendicular to one another. These are the free body diagram arrows, same as force diagram arrows. Okay, what do you mean by the arrows? You mean direction? Yes, the directions are the same. Okay, however, right, this is our normal force, okay, perpendicular to the surface. If we get one force wrong, is the whole thing wrong? No, not at all. You get a mark per force. So if one force is wrong, you're going to lose 1 mark. Horizontal axis, vertical axis. Are you guys with me? Okay. Yes, it represents the incline technically. This is the floor, and this is at you don't have to put this angle. I'm just showing it for you guys. This is at a 45-degree angle. Okay, the incline. That's why I'm just the horizontal, your horizontal axis, when you are working with the questions, always needs to be parallel to the surface. And then you draw your vertical. Because we are now on an incline, we are not on a flat surface anymore. Very important. Okay, so that is why we are doing it on our free body diagram. And you're going to see it's going to help us also when we do separate it into its components. But for now, while we're not separating it into its components, it's still helping us. Okay, so that's normal force, which is up away from the surface. It's always up away from the surface. Okay, in this case, it's technically not up, it's more like up left, but it's perpendicular to the surface is the best way to describe it. Perpendicular to the surface. Okay, I'm going to leave that there as well. You don't have to put it. I'm just leaving it for understanding purposes. Okay, let's do the next force. The next force can be our tension going up the slope. And now this is easy to draw because it's in line with our surface. Okay, so this is our tension, F tension. In line with our surface, up the slope. Okay, this could even be represented here. Okay, but that's fine. There we go. Up the slope, tension. Okay, lastly, friction down the slope. So opposite, directly, obviously you're going to use a ruler. So yours are going to be even more straight than mine because mine are not even perfect, right? But friction would be down the slope. Now opposite to the direction of that tension, just like this. Call this frictional force. Okay, and that's our free body diagram for the 5 kg object. Again, you can leave your dotted lines in. It's going to be in pencil. And then everything else you're going to put in pen, like your forces. So even if you'd like, you can put the angle. It's not necessary, but you can put the angle if you want. And as you can see, none of my vectors are equal in length, so I didn't measure them because look, I don't even have the value of tension. I don't know how big is tension. I don't know how big is normal. I don't know how big is friction. I don't know how big is FG even yet. I don't even know how to compare them. So their lengths, you don't have to worry about. The arrows, of course, are important. They have to be in the correct direction. They all stem from this circle. However, with the force body diagram, we draw them as such. Okay, one more time. FG from the center downwards, Fn from the surface, perpendicular to the surface, up in the upward direction. Friction on the surface as well, but the whole thing is on the surface at the back of the object, meaning opposite to the direction of motion. And tension or applied, any sort of tension or applied is generally on the object. Wherever the tension rope is connected, you can basically represent it at that part of the object. Okay, and then yes, free body diagram, all from the center dot. Okay, and we just need to represent their directions accurately. Okay, cool. So what we'll do next week is we will continue with this, right? Are we going to have extra lessons for physics? Okay, it should be discussed with you guys in this week. There's nothing certain, but yes, grade 11. Yes, they might be. Okay. How do we do it for the 3 kg block? Okay, look, I don't mind doing it if you guys are down to stay. I can do it quickly for the 3 kg block instead of doing it next week. So next week, what we'll do is we'll continue with this question, which basically incorporates Newton's 1 and Newton's 2, Newton's first law and Newton's second law, move on to equilibrium, and then eventually I just want to get to this question itself, which we'll do. Okay, so yes, okay, let's do the 3 kg object. For those who need to leave, you may leave. For those that can stay, you may stay. I'm going to continue just to finish this up. It won't take too long, but if you need to leave, you may leave, and then you can watch it later. Okay, so let's do for the 3 kg object. Just going to copy this. So 5 kg object. Now let's do for the 3 kg object. Does the arrow have to touch the line? Yes. I wouldn't see why your arrow is not going to touch the line. Yes, make it touch the line. Make your free body diagrams neat, please. Make it easy for the marker to mark. Use a ruler. Don't give the marker a reason to make you lose marks. And Newton's laws, the one given by the government, was our teacher said, you have to know definitions as per request from the government in parrot fashion. Okay, so they might be slightly different. What I would recommend for definitions, so utilize my notes for general understanding of definitions. They will not actually be exact. I noticed that these notes that I use for definitions are not exact. They are very similar. What I would recommend you use for definitions are your marking guidelines. I will put the marking guidelines in the Google Drive as well. Okay. I'm pretty sure you guys have marking guidelines in grade 11. Okay, so let's do for the 3 kg object, right? So let us I want a list. Okay, so by the way, this guy right here, okay, is for 4 marks. You get a mark per force. So if you break down FG into its components, you're not going to get an extra mark. You're still going to get 4 marks. Okay, hint, this guy is for 5 marks. Okay, so I want, what are these laws correct according to government? Yes, they should be. But like I said, if you're saying like for example, your teacher said, study parrot fashion. Yes, I agree with them. You should study it like that because they're going to ask it and you need to know the exact answer, which are from memos. Okay. If in that case, if you're going to look for that specific exact definition, the wording of those, you use the marking guidelines. And I'm not talking about marking guidelines as in a memorandum for a test. I'm talking about a document called the grade 11 physical science marking guidelines. It's just like a breakdown of all the topics, and it has all the definitions inside there. So that's the document I'm talking about. That's directly from the government. So yeah, you can utilize that. Yes, okay. So we need 5 forces. Yes, one person gave everything. Thank you very much. Fn, F applied, F friction, Fg, perfect. That's all of them, right? So let's take care of that. Firstly, it's a force body diagram. So I am going to do my object with my surface, and I'm going to do my Fg from the center going down. That is something like that. Fg. That's the game. Okay. So Fg is going straight down, right? Then we have tension. Okay, let's do normal force, okay, which is going to be the same for the 3 kg object on the surface going up. So we do it here. Perpendicular to the surface, and I call this my normal force. Thereafter, so it's all the exact same, except one is different. So then I have my friction as well on the surface, away from the object, away from the direction of motion, F friction. Then we have tension. Which direction is tension for the 3 kg object, people? Yes, correct. Down left or down the slope. Good. Down left or down the slope. Not, yeah, down left, correct. So down left or down the slope, tension is connected somewhere there. So that's what I'm going to do. I put my tension going downwards. I'm just going to make it the same size as friction just so it looks nicer. Not for its magnitude. Call this F tension. It's not perfect, but I mean, life is not perfect. Applied force. Okay, so now the applied force is not even up the slope. Okay, it's upright, but now it's 20 degrees more upright, 20 degrees more up compared to up the slope. So for this one, we have to try and be a bit more specific and help ourselves by creating a small dotted line for the sake of creating the angle. So a dotted line that's parallel to the surface, and then another dotted line indicating to us the angle. It's not compulsory to put the angle, but I would, just to make it neat, so that it's more specific. Okay, this is 20 degrees to the 20 degrees more up, instead of just it. Is that in line with the surface? Is it more up? We have an applied force, just like that. F applied. Force body diagram. How did you get to 12.5 kg as the mass? Okay, I'll go through that. Other lessons going to continue next year. I hope you're not planning to fail, but I'm not 100% sure. Let's hope. Let's see how this year goes, how successful we are, and we might continue next year. 3 kg object, free body diagram. Okay, 5 marks as well. Okay, force body diagram, done, all the forces. Okay, if you guys haven't, I want to give you guys a chance to try this. I'm going to give you like 2 minutes to do it yourself if you have paper or some way, if you're going to do it mentally, but try and get paper just to do it, and then I'll do the correct one, and then we can mark it. Okay, so I want the 5 forces in a free body diagram of the 3 kg object. Done. Okay, like few seconds more. Done. Can you please zoom in on the force body diagram? No, you have to use this. I cannot zoom in on the force body diagram. Use this diagram. And normally, like, you don't draw a force body diagram first and then draw the free body diagram. You do either one. So they'll tell you most of the time you actually do free body diagrams, but sometimes they'll ask you to do a force body diagram and you need to know how to do it. So yeah, sorry. So you'll need to, okay, seems like almost everyone is done. So you'll need to, you'll need to know how to do them individually either way. Okay, so firstly, my little dot. Okay, step number 1. Who failed step number 1? Please tell me. Dotted lines. I hope we draw axes with a ruler. Okay, so yes, I presume 99% of people forgot about step 1. Okay, trust me, it's just going to make your life a little bit easier, especially when it comes to the hard questions. A lot of the stuff I teach always seem easy when it's the easy stuff and then no one listens. But when it comes to the hard stuff, because it simplifies things, it makes the hard stuff easier. Okay, this is so skew, but there's like, if I'm going to draw it again, I'm going to draw it skew again. Okay, so firstly, we're going to draw FG going downwards. Happy days. Secondly, I'm going to draw F normal perpendicular to the surface. Okay, in the upward direction. Thirdly, I'm going to draw my friction okay, which is away from the direction of motion. It's kind of skewed, so I'm just gonna correct it. Okay, whatever, we'll just do that. Okay. Pretend that that's not curved. Okay, we have frictional force. I can then draw my applied, which is actually 20 degrees from my surface angle. And finally, I have my tension as well, which is down left. So there's two ways to do this. The way I prefer is to just go over that and create another one. And then you have F tension. Okay, the second way you could do it, I'll draw it on the side, is, so there's two ways, I'll draw them both again. One is you have a big dot. Second way, you have a big dot and then you just create, okay, a tension and a friction, both in the same direction. I don't like this way because it's just like untidy. You just have like your FG, you have your FN, you have your F applied. Okay, and then, or you could just do that, whichever one. Okay, both are going to give you 5 marks. You must out one, you must out 1 mark. Can you do either or? Yes, you are free to do either one. Okay, cool. So that's done. Nice. Okay. Post body diagram, free body diagrams for 2 objects. You resolve the F applied. You mean, do you separate into its components? That's what you're referring to. Yes, you would resolve it. Instead of friction, can we say that the force that the 3 kg acts on the other object? Instead of friction, can we say the force that the 3 kg acts on the other object? No. No. That's different. That is different. That's when 2 objects are touching. I think you're talking about when 2 objects are touching. Friction, on the other hand, is due to the surface. It's between the object and the surface. So as long as there's an object touching the surface, there's going to be friction. It's not the force that the 3 kg object is exerting on the 5 kg object. That is when they are touching. That is Newton's 3rd law, which we will get to. In this case, they do exert a force, but it's in the form of tension. How do you know that there's an F applied? Because the question says F applied of 120 newtons, just like that. In the question. Okay, any other message? Any other questions? When we were getting a time, that's a good question. I was thinking about it today. Okay, I know I said last week. Let's see if we can create one this week. I'm just a bit skeptical because it's a bit difficult to because we just started with the time given. It's a bit difficult to discern when we're going to finish which topics. Okay, for now, what I'll do is, instead of just giving a set timetable, I'll just give you guys a list of the order in which we will be covering topics. Is that fine? Is that better than nothing? Does that help you guys? I can just create something to just give you the order in which we will doing topics. Will the times be the same during Ramadan? Probably, because it doesn't interrupt anything. We'll see. With Ramadan, we will accommodate accordingly. Yeah, you can do that object on a flat surface. Between any 2, whenever you have tension in a rope that's connecting 2 objects, you can put an X. It's not like important or mandatory. It's just you cutting the rope. You're ignoring the rope and you're just representing the tension there and tension there. But you just need to know another explanation. Like I said, the tension is where the rope touches the object, you start there and go away from the object. That's your direction of tension. Okay, cool. If that is all the questions we have, then we can end it. Okay. I mean, no problem. You guys are welcome. So you're talking about this notes, or you're talking about notes that I'm using? I can send you the notes, the separate, the tension between the two objects. Yes, the tension between the two objects is equal. Thank you. You too. You're most welcome. You please send us the notes so that we can do it with my notes. Are you talking about? Oh, I see. Okay. You're talking about sending it beforehand. Okay. I get that. Okay, I can do that. Sure. No one else requested it, so I'll kind of just do it for this class for now, and then how do we calculate the tension between the two? That's a story for next week. We will do a question. We will go straight into this question. Yeah. Also, we'll just send a memo for this question as well. Yes. Okay. So these questions here we will do. So you will have the memo as well as the video memo because we'll do it together. Whichever ones I don't do, I will send the memo for. Whichever ones I tell you to do yourself, I will send the memo for. Okay, cool. So let's end it there. Thank you guys so much for joining. I hope that you guys enjoyed it and benefited. All the best for your guys' week at school. And I will see you guys next week, same time. Thank you guys so much.